previous lesson, we looked at rate laws, and we looked at rate constants, and we talked about orders, but we mentioned that you have to experimentally determine those rate laws. You can't just look at a reaction and know what they are. So in this lesson, we're going to have the learning objective of trying to see how you take experimental data and obtain a rate law. In other words, obtain the orders of the reactants by using that data. And the best way to demonstrate this is with an example, and so we're going to do a couple of worked examples as we go through this process. Here's our first reaction. We are reacting NO and Cl2 to produce NoCl. We know that the rate law will take on the form of a rate constant, which we use a lowercase k, times NO raised to some power, and we'll call it x. I don't know the power. And Cl2 raised to some power, I'll call it y. I don't know the power. My goal is to determine those two powers. So for x, what we want to do, in other words, it's the order of NO, we need to choose experiments that hold chlorine constant. Now what this does is it takes chlorine's effect out. As we run these experiments, and I want to number them 1, 2, and 3, as we run these experiments, by holding chlorine constant, we can see how did the changing of the concentration of NO affect the rate, and from that be able to determine the power. So we're going to be looking at experiments 1 and 2 for this. Take a ratio of the rates for those two experiments and a ratio of the concentration of the NO for those two experiments. Okay, so that's what we're going to be doing. Now I generally like to take large divided by small because it keeps me from having to work with fractions. And that value is essentially 4 for the ratio of the rates. Now I'm looking at the concentrations up here again in these two values. I take the ratio of rates. Now make sure you do it in the same order as your ratio of rates were. We're doing a ratio of concentration here. I had done experiment 2 over experiment 1. Make sure you do experiment 2 over experiment 1 for this portion as well, and that gives me 2. Now what do these numbers tell me? I am doubling the concentration, there's the 2. I am doubling the concentration of NO, and I'm seeing a quadrupling in the rate. So we say 2 to what power, that's my x, will give me 4. And certainly x is going to be 2. If I raise it to the second power, it fulfills that, and that tells me now that the order of NO is second order, and I can put a 2 there for that. Now we're ready to look at Y, the order of chlorine. Again, we want to choose experiments that hold the other substance constant. So we want to hold NO constant. So look at that data and decide which experiments do that. Well, I see, and I want to just erase these, get them out of my way here. We see that NO is being held constant in experiment 2 and 3. So once again, for these two experiments, we're going to do a ratio of rates and a ratio of concentration for experiments 2 and 3. Again, I'll choose the large number divided by the small number. In this case, it's essentially 2. And in that same order, that was experiment 3 over experiment 2. So make sure you do concentration, experiment 3 over experiment 2. It won't always be larger over smaller. It is in this example. Okay, so now we see that this is telling me that as I double the concentration, I will double my rate. And so we say 2 to what power gives me 2? Well, y is certainly equal to 1. So now we know that it is first order in chlorine. And we could write the finished rate law to look like this. Rate is equal to K NO squared Cl2, and we don't write the first power. What's the order overall? Well, it's third order overall. Sometimes you'll be asked then, well, what is the value of the rate constant K? And to do this, you choose an experiment up here, you plug in what you know and solve for K. To get a real good K, you do it for every experiment you run and do an average. We're not going to calculate that on this example, but we will learn to calculate K in the next example. Okay, so here's our second example. This one's got a little bit, some different features. One of them is this little thing sitting up here over the arrow. That is a catalyst. And a catalyst is something you add to the reaction to speed up the reaction. It does not get consumed, so it's not written as a reactant, but it could, its concentration could affect the rate. So we see that in our experimental data, we not only have the reactants OCl minus and I minus, we also have included in here some data about OH minus's concentration and how it affects the rate. So the general form of the rate law will be rate is equal to K and the reactants OCl minus raised to some power, the reactant I minus raised to some power, I'll call it Y, and the catalyst OH minus raised to some power. Now if it doesn't have any effect on the rate, it'll end up with a zeroth order, but that's looking a little messy already, so I'm going to erase that out and rewrite OH minus raised to the power Z. So we can determine that. So part A is asking me to determine the order, in other words, X, Y, and Z for this. So we're going to follow a similar procedure, but it's a little bit more complicated. So for X, X was the power for OCl minus, Y was for I minus, and Z was for OH minus. So I'm going to write those up there. For X, what we need to do is we need to hold the other two substances constant. So we need to hold I minus and OH minus, both constant. I'm going to write in black instead of this thick pen here. Hold I minus and OH minus constant. So look at that data and see which two experiments you'd like to choose. It looks like we could choose experiments, let's number them. What would that be? Experiments 3 and experiment 1. Experiment, I'll write it 1 and 3. Hold the I minus and the OH minus constant. And then we'll do a similar work. We're going to do a ratio of rates and a ratio of concentrations. Ratio of rates. 4.8 times 10 to the minus 4, that was experiment 1, divided by 2.4 times 10 to the minus 4, that's experiment 2, and that gives me a value of 2. Ratio of concentrations. We have, for experiment 1, 0.0080, for experiment 3, I said 2. It's a 3. For experiment 3, it's 0.0040. And this is also equal to 2. So a doubling of the concentration yields a doubling in the rate. 2 raised to what power gives me 2? Well, X is equal to 1. And now we know it's first order in OCl minus. Okay, now let's do it for Y. For Y, we need to hold the other substances constant. So we need to hold OCl minus constant and OH minus constant. And let's figure out what experiments do that. I see that experiments 2 and 3 hold OH minus and OCl minus constant. So I'm going to be looking at experiments 2 and 3. And we'll do the same process, ratio of rates and ratio of concentration. I'm going to do 5 times 10 to the minus 4 over 2.4 times 10 to the minus 4, and I'll get essentially a 2. It's not exactly a 2, but it's experimental data. It's close to a 2. It's close to a doubling of the rate. And then I'm going to do a ratio of the concentrations. Now, I did experiment 2 over experiment 3. Make sure I do that same order here. We have 0.0080 and 0.0040, and so again have a doubling. So doubling the concentration raised to some power will give me a doubling of the rate, and so that tells me that y is equal to 1 as well. So now I know it is first order in I minus. Now we're ready to do z. What do we need to hold constant? Well, z is OH minus, so we have to hold OCl and I minus constant. Which experiments do that? Well, you might be able to find a couple of them that do that. I'm not sure, but it looks like to me it could be this one, experiments 3 and 4. Okay? Experiments 3 and 4 meet that criteria. So let's do a ratio of rates and a ratio of concentrations. I'm going to do large over small. 4.6 times 10 to the minus 4 divided by 2.4 times 10 to the minus 4, and that's close to 2. Now this was experiment 4 over experiment 3, so let's make sure we do the same order for that. Experiment 4 is 1.0, experiment 3 is 2.0, and we end up with 1/2 or 0.5. Whichever way you want to think about it, one or the other. Okay, so now we have to say to ourselves, 1/2 raised to what power gives me 2? Well, that would be -1. So here's a case where we have a negative power. We know that 1/2, when you raise something to negative power, you're taking the reciprocal. So that would give me a value of 2. So now we know up here that it is -1 order for z. So our generic form of this rate law so far takes the form, it's no longer generic, it is actually the rate law. K OCl minus I minus and OH minus to the -1. Now what I want you to do is determine, we go back here to the previous question, part B says write the rate law, which we just did, and determine the value of the rate constant K. Now to determine the value of the rate constant K, you can take one of these experiments, plug in the values, and obtain a value for K. I want you to try to work on that and come up with an answer to this question. Now if you picked number 3, maybe you only picked it because you see right here that that matches the rate law that I did before, but this would be the same thing, wouldn't it? A -1 would be to put that in the denominator. Those are equivalent at that point. You probably came up with a value for 30. Those are equivalent there. The only difference between these two answers comes in the form of the unit. So let's think about the unit for just a moment. We know that rate was equal to K OCl minus, well, I've got it written right there. I don't need to write it all again, do I? Let's look at the units of these things. Rate is in units of molarity per second. K we don't know, we're trying to determine its units. OCl minus is molarity, I minus is molarity, and OH minus is molarity to the -1, or 1 over molarity. Now if we take all of these units to the other side, we'll have K is equal to, I'm going to take each one of these over, so I'm going to divide by that m, so I have m over s. Dividing by that m, I'm dividing by this m, and I'm multiplying by that m. So the molarities are canceling, and I'm left with seconds in the denominator. Now what's the overall order of this reaction? Well, it would be 1, the order of OCl, 1, the order of I minus, and -1, the order of OH minus, for an overall order, it's first order overall. And what I want to tell you that you probably need to put to memory, but we'll mention it many times, is every time you have a first order overall reaction, that will be the unit of K. Every time. If it's first order overall, the unit of the rate constant is always 1 over seconds. Okay, so we have gone through our learning objective. We have taken experimental data, and we've used that experimental data to come up with a rate law for the reaction. Now, we also took it one step further. We determined the value of the rate constant, but know that this rate constant only applies to the experimental conditions that that reaction was run under. So whatever its temperature was, that is the rate law, its rate constant value.